Hello, my name is Scott Grizzard. This is Calculus 1 from the University of South Florida. Welcome. Couple things. Today we're talking about the Fundamental Theorem of Calculus. The notes for this class I put on my public web space. Let me pull that up again. The notes for this class, I'm going to post this in Twitch chat just in case people that are not, I know that there are a couple people that aren't in my class that are at other classes that are watching this. So I'll post the notes for today in Twitch chat so you can click on them. They're also posted in Discord chat if you'd like to see them there. Those are the notes with all the details. And I fixed 4 typos this year. So, I actually went back and fixed typos on this year. So exciting stuff. Are there any questions before we begin? Obviously, I'm asking those questions on Discord chat. On Discord chat. Are there any questions on Discord? No? Okay. Well, today we're going to be talking about the Fundamental Theorem of Calculus, which is a beautiful, and I hate the fact that Trump is now out there going, it's a beautiful thing and all this stuff. No. There's a real aesthetic pleasing quality about this proof. It's a beautiful proof. It's one of those proofs that makes people want to go, be math majors. It's so beautiful. And it's a big picture proof. It's easy to get lost in the details. And this is truly a big picture proof. You want to keep the pictures in mind. Okay? So we're going to go over it. As usual, though, let's start by going over the quiz. Here's the quiz for today. So, state the fundamental theorem of calculus, as usual. How do we feel about problem number 1, 1 to 5? Okay. We comfortable with that? We've only got one more quiz for the whole semester, and guess what? It's there too. You could have used this version. You could have used this version. Either version is fine. This version right here is perfectly fine as well. Whatever version you want to, as long as it's got the big detail, the important details, the f is continuous, the g prime of x equals f of x, that again can go there. The derivative of the AUC function is just f of x, and the AUC of fa of x is g of x minus g of a. Or in integral notation there. Okay. This one's a little bit trickier. I can never remember this cold. And even after teaching calculus as many semesters as I can still never remember this thing cold. I have to draw it out. Okay, so what I do is I draw this little picture here. Okay, and then from that picture, I build my definition. So I've got, change in x is the width. I'm going from a to x, or change in t, either one. And again, the big idea is I don't memorize the theorem. I memorize the picture. I don't know why this thing doesn't want to multi-select. So the big idea here is I don't memorize the definition, I memorize the picture. And then I use the picture to build it, right? So here's f, and then I've got this little rectangle here. I'll put it in blue so I can keep track of which one's which. Oops. I've got these little rectangles here, and these rectangles are what I remember in the theorem. And so I do that. And here I'm going to use, it doesn't really matter which one I use because I told you it didn't. as I said, I remember the picture first, and then I draw my rectangles, and then, okay, the area of that rectangle is this, 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 and then what I do is I just write it out. And so this is the limit. I use the right sum. You can use left sum. That would be tk minus 1. You could use midpoint. You could use the lower. You could use the upper. It's all up to you. 1 to 5, how do we feel about this statement? Question 2. And one thing you can do, if you mess it up, draw your picture. Because if you draw your picture, 1, you can remember what it is. And 2, you can also get, you can remember what it is. And 2, heaven forbid, you might, you get a few points if you draw a picture and you can't remember the rest of it. I could also write it another way if this makes you feel better. I could also have written it like this. The integral from a to x f of t dt equals t naught times change in t plus t1 times change in t plus dot 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 plus t, here I'm using left, n minus 1 change in t. And then I put the whole thing together and I say the limit infinity of that, where this thing and I could have done that as well. That would have given me the exact same answer. So it depends how you feel about it. This is just the fact that what I did was take an infinite number of Riemann sums. And I even ditched the summation notation. Okay, so either one works. The important details are that you define these things. You can define these things several different ways. Right here I defined it where it was a plus n change in t, which is the exact same thing I would get if I did this. I'm sorry, that shouldn't be n, that should be k. I would get the exact same answer. All right. And I admit, it's easy to get, again, draw the picture and then use the picture to build the details. Okay. For question 3, what I'm going to do here is I'm going to draw a chart. This is I've got antiderivative problems. The first thing I do, I'm going to show my thing to the computer, the Proctorio. I'm going to show my blank pages to Proctorio, and then I'm going to write down my chart before I do anything else, right? I'll use a scrap piece of paper that I show up to Proctorio as blank, and then I write this. I just dump this method here. I take all my g's, and then I take their derivatives. So I've got sine, the derivative that's cosine. Cosine is negative sine. That means that negative cosine is sine. And that's the order that I build these in. This means this. Arc sine is that. Arc cosine, the derivative is that. Arc tan, the derivative is that. E, the derivative is that. Ln, the derivative is that. 1 to 5, how do we feel about this idea of just writing down a chart before I even start these problems? Okay. Now that I've got the chart, I look at the chart. Well, 1 over the square root of 1 minus x squared, there it is right there. It's arc sine plus the c. If I take the derivative to check, I probably wouldn't do this because there's nothing but the antiderivative. But I take the derivative to check. And I get the same thing. Okay. How do we feel about question 3a, 1 to 5? Okay. All right. All right, moving on. This one's a little trickier. What I'm going to do when I see this, okay? The first thing I'm going to do, it's an integral problem. The first thing I'm going to do is look at my chart. So I run back up here and I look at my chart, and it's not there. I don't try to flip it. I don't try to use this, okay? I look at my chart and say it's not there. So now I look at this equation. Well, if that's why, I'm going to graph this equation just to kind of get an idea of what's going on. I'm going to draw a picture. And when I draw a picture of this, I put 0 here, I put 1, -1 here, 1 here, and I look at this picture, and I'm going to look at this thing and I'm going to go, wait a minute, this is a circle. And in particular, what I'm looking at is the top half of a circle. And it's a circle with radius 1. So how do we feel about the fact that this thing represents a circle of radius 1, 1 to 5? How do we feel about that idea? Okay. Well, I want the integral, and integral is nothing but area. So what am I going to do? Well, I'm going to draw it, and then I'm going to shade in the part that I want. Well, the part that I want is from -1 to 0. So that means I want a quarter of a circle with radius 1. I want to go from -1 to 0. I shade that in. I'm looking at a quarter of a circle. That's 1/4 pi r squared. R in this case is 1, so I wind up with pi over 4. Okay. Any questions? Please, again, type your questions in before I ask you any questions, because obviously I can't, it takes you a while to type. So I want to make sure that that's good. All right, for part C, I'm just going to treat this like it's an antiderivative. I can split it up formally like this. This one I probably wouldn't. You don't need this step. This step is fine. What have I got here? I got 4x. The first thing I'm going to do is deal with the exponent. So what I do is this is x squared, and then I look at this 4. Well, to get to that 4, I would need a 2 out here. So I put a 2 out front, and now when I take the derivative, I would wind up with 4x, which is what I want. Plus, now, for this positive sign, this is one reason I make the chart. Positive sign, negative cosine. So I'm going to put my negative cosine in for that. E to the x, e to the x. And then, of course, my constant. Now I take the derivative to check, and I wind up with 4x to the first. Plus, I wind up with minus sine of x, so plus sine of x, minus e to the x, plus 0. How do we feel about that one, 1 to 5? we got some breakup. Okay. Any questions about this? Issues, thoughts? Okay. Well, the next one, what I'm going to do, notice here that I'm going over the positive region, right? I'm not crossing zero. That's important. If I was crossing zero, this would not exist. I'm not crossing zero. So I'm just going to take an antiderivative. Any antiderivative will do. I need the one, though, for x greater than 0. That's log of x. I apply the Fundamental Theorem of Calculus Part 2, and I get g of e minus g of 1, which is the natural log of e minus the natural log of 1. The natural log of e is 1. The natural log of 1 is 0. So I wind up with the number 1. How do we feel about this, 1 to 5? This is part D. All right. Okay. That's the quiz. Your next quiz, I haven't finished it yet, but I should today, and will be posted online. Are there any questions, comments, or issues? Okay. Before we get started, I have a few announcements. Some people are asking questions. Some announcements. So I sent this out to you already on Canvas, but the Wednesday night review will be at 7 this week and not at 5. That's because and it's the test review. The reason why is because of is because discrete math is taking their test. Now there's the question: what would be the definition of an integral on the closed interval? That would be the Riemann sum. So the answer to your question is question number 2 on here. How would you know to take FTC1 versus FTC2? FTC1 you use when you want to take the derivative of something. FTC2 is what you use if you want to compute something. So if you're taking a derivative, that's FTC1. If you're computing an integral, that's FTC2. Okay, are there any other questions? Okay. All right. So what we want to do, last time we talked about the properties of integrals. Today, what we're going to do is we're going to prove the fundamental theorem of calculus, part 1 and part 2. Okay? FTC2 is actually just an easy corollary of the thing. Now, the big idea of this is it's a proof in pictures. Okay? Don't get caught up in the details. Focus on the pictures. I cannot stress this enough. The whole thing about this proof is that it is a proof in pictures. Okay? What we're going to do is we are going to prove FTC1, and then we're going to prove FTC2 using FTC1. Now, your book does this proof also, but before it does this, it does the proof of FTC2 first, and then uses that to prove FTC1. And then it oh, by the way, you could have just done FTC1 without that. Okay? We're doing the by the way proof because it's the better proof. FTC2, if you want to do the proof of FTC2 without FTC1, you have to use the mean value theorem, and it's ugly. It's like this you're taking this giant sledgehammer called the mean value theorem, and you're beating this proof into submission repeatedly. And it's, you're basically taking an infinite applications of it's an ugly proof. Okay? It's not pretty. This proof is beautiful. Okay? This proof is, the whole thing is 2 pictures. So how do we feel about that 1 to 5? This is a beautiful proof, and if you don't think this proof is beautiful, I'm going to be upset. Okay? Don't 1 to 5 that. That's a joke. Okay, well, fine. 1 to 5 it anyway. Now, The idea about this thing is that it's pictures, so don't get bogged down in the detail. All right, what I want to show is I want to show that the derivative of this thing right here, of the area, is f of x, where f is continuous. Okay, now I don't want to write this. So what I'm going to do, I don't want to write this statement here. So what I'm going to do is I'm going to say a couple things. Let a of x equal the integral from a to x of f of t dt. All right, that's the same as AUC A. Okay, I don't want to write that all the time. Okay, now, recall the definition of the derivative. So here's the first big idea. And it's really the big idea of the whole thing, the picture. What I want is a marginal type of rectangle. Okay? So let me show you what I mean by that. So I have this function called f, and it's just running around hunky-dory. It's continuous, but it's just running around something like this. I don't really care what it looks like. I only care if it's continuous. I'll put the strategy in later. Okay. Now, this thing that I'm talking about, it goes from A, there's an X, and then there's this X plus H ahead of it. So the distance from here to here is X plus, is H. And what I'm interested in is A of X plus H minus A of X. Okay? Well, A of X plus H is all this area in green here. Right? That is the area under the curve, under F, from A to X plus H. How do we feel about that 1 to 5? And then A of X is this area in pink here. All right? It's the area from here to here. How do we feel about that 1 to 5? right? It's this area here. Okay. So the question is, what is a of x plus h minus a of x? That's this area right here. This here let me get another pen. Orange. That's this here. This piece here is a of x plus h minus a of x. How do we feel about that, 1 to 5? In other words, I don't actually care where a is. I want this area right here. Okay. Well, this area right here is the area from x to x plus h of f of t dt. Okay. So our conclusion from our first picture is that a prime of x equals x to x plus h f of t dt. All over h. And this bit up here I'm going to call the marginal rectangle. Okay. All right. So that's the first part of the proof. That's the first picture. Okay. Now what I'm going to do is I'm going to zoom in. I'm going to zoom in on this marginal rectangle. So I'm going to take it and I'm going to zoom in. Right? I'm only going to view this piece. Okay? I don't care about this piece anymore. The only piece I care about is that piece. Okay? That's the marginal area that I'm interested in. Okay? Yeah. Need my mouse. It's a bad idea putting that on the floor, but I'm going to do it anyway. Oops. So now what I'm going to do is I'm going to zoom in on this picture and only look at that. Let's redraw the picture down here. All I'm doing is I'm zooming in here. All right. I don't know why that's happening. There we go. All right. And the area I'm interested in is, again, this orange area here. I failed kindergarten, you can tell. There wasn't enough math involved. Actually, there was. They just didn't tell you it was math. This right here, this orange area, is the integral from x to x plus h f of t dt. And what I want to do is I want to get an estimate on it. I want some way to get a handle on that area, because this thing can be really squiggly, like it is where I drew it. Well, go back to your... So how do we feel about this idea, 1 to 5? All I've done is zoomed in. Now, if we go back to the definition of the Riemann integral, okay, we had, let's see, we had right estimates. They would sometimes give me an overestimate and sometimes give me an underestimate. I had left estimates, but again, sometimes I'm over and sometimes I'm under. But look at these. What about the low? Is the low always an underestimate? It's consistent, right? I could never get an overestimate by taking the lower integral. Likewise, I can never get an underestimate by using the high, by using the upper integral. Okay? How do we feel about that? 1 to 5. If I use the lower, I always get under. And if I use the upper, I always get over. Okay? And that's the only reason why we do uppers and lowers, because it allows us to control which direction I'm messing up in. All right? It tells me that whatever my estimate is, I always wound up with an overestimate, or I always wound up with an underestimate. That's the only reason I care. So what I'm going to do is I'm going to do this. I'm going to draw a lower rectangle. I want an idea for this. So I'm going to draw me a lower rectangle. There's a lower rectangle. And this right here, right? My width, by the way, is H for width, because it's French. It's h for width. This right here is the lower rectangle. Its height is min fx x plus h. And its width is h. Well, of course, what's the natural thing to do next? The next thing we want to do is we want to divide the upper rectangle. We'll do that in green. All right. How do we feel about that? 1 to 5. I now have something on the upper and lower, right? We had this definition. Remember this min max business that we did? We had this function called min and this function called max. This was right before text 3. And what we did was we had this function that would just stay at the max, and this function that would stay at the min, and it gave us these nice continuous functions. Okay. All right. Okay. So apparently I've got 2 voters now in chat, and everybody else is like not doing anything. So thank you, you 2 voters in chat. I don't know what happened to everybody else. So okay. Well, that means that this area I'm interested in is trapped between the upper and the lower. Okay. This upper rectangle here and this lower rectangle here have the following, right? The first one, let me move this out. This upper and this lower rectangle here, I've got that I've got that min fx of x plus h times h. This is the height. Sorry, this is the width, h for width, and this is the height. Is less than or equal to the thing I'm interested in, okay? And this is true, by the way. all h near 0. It's actually true for any h. Now, okay, how do we feel about this statement, 1 to 5? I just combined this idea. I've got an area, right? This is the area of the upper. This right here is the area of the margin. And this right here is the area, the area of the lower. The area of the margin, and that's the area of the upper. Right? Okay, well, what am I setting up? All right. So if h is greater than 0, detail, detail, detail. Boring detail. I divide through by h, I preserve the sign. If h is less than 0, I do the exact same statement but flip the signs. Okay? How do we feel about that, 1 to 5? With boring details. I actually don't, I'm not completely interested in how you feel about that because that's nothing but boring details. But, how do we feel about it? I'm not really using the whole board space on it, are I? This should actually go over here if I want to use better board space. Oh, well. Okay. Well, I've kind of given it away now, right? So, since f is continuous, max and min are defined. That's the EVT. And continuous. So the limit as h goes to 0 of min fx of x plus h equals, by direct substitution, the min fx equals x plus 0, which equals min fx of x. Now, what is the min of fx of x? Okay? So let's go back and let's look. If I don't go anywhere, okay, if my base point is exactly the same as my x, what is the only option for the min? There's only one thing it can be. I haven't gone anywhere. And because I haven't gone anywhere, it's just f of x. 1 to 5, how do we feel about that? If I take the limit of this thing, right? If I'm sitting here at my base point and I take the minimum over an interval of nothing, right? Okay? So if I take this base point, if I haven't gone anywhere, if I have gone nowhere, then the min f x of x equals, well, by the definition of the thing, the minimum of the equation f of t such that t is in, well, x. In other words, t, there's only one option for t. It's x. Right? This closed interval is just the singleton x equals f of x. Okay. I've gone nowhere. Right? My interval has no width. The only element in this set, is x. Right? I'll even write that. Right? There's only one element in the set. I've only got the singleton x, therefore it's got to be that. Likewise, how do we feel about that? Little two cops action right there. 1 to 5. And again, these are details. Focus on the big picture. This is all just details. Okay? What's really key for this whole thing is this picture. Yeah. So someone's cat is, yes. Well, thank you. I'm glad. I want to say your name, but I can't on Twitch. So I'm glad that it's, brings it all over a circle. One of the other instructors says that I love this proof because it wraps up the course in a nice little bow, right? I took one end, I took the other, and I went. So it's a nice way to kind of conclude. We will have class, by the way, on Wednesday. There is stuff on Wednesday, but that's kind of the whole thing. And this is the whole idea is this right here, is this picture. These two pictures, that's what you need. You need these two pictures. The idea that what I'm after is this marginal area, and then this idea that I take the something above, something below, right? These two rectangles, and I just squeeze two cups. As this thing, as h goes to 0, the min function on this is going to go boom, and the max function on this is going to go boom. Talk about that in a minute. Actually, you know what? I don't think I will. I'm going to talk about that in review. So, any other questions? Okay, well, we did FTC 1. Let's just do FTC 2. And again, big picture. Focus on the two. Let's write a little strategy for this. What am I going to do? Let's add a little space here. What am I going to do here for the strategy? I lost the H. What is my strategy for this proof? Okay. This is the first one. I'm going to, what? Use this picture to show that. 2. Use a picture to get upper and lower rectangles set up and apply 2 comps. And that's it. That's all I'm doing here. This is the strategy for FTC 1. And I'm going to use a picture to show what I'm after is the marginal area. I'm going to use a picture to get upper and lower rectangles for this marginal area. For the marginal area, I'm going to set up and apply 2 comps, and boom, I get it. 1 to 5. How do we feel about this now? Okay. And there's extreme beauty in this idea. This idea that all I do is I draw a picture, and what am I after? I'm after the marginal rectangles. So there's extreme beauty in this idea that as I sweep across, each one of those little marginal rectangles of my area, all I really need is the height, and the height is f of t. That at the margin, that area of that marginal area, the area of that marginal little slice, okay, the area of this marginal little slice as h goes to 0 is the height. That's the big idea. Okay. So the question is, in this case, if we blank on the test and draw the pictures, they'll actually be more helpful than before. Well, I thought they were helpful last time, but this proof is the two pictures with, some filler. The whole proof is the two pictures, two cops and a drunk, and the details that you just kind of, when someone asks me this proof and I'm not presenting it for a class, if someone asks me, hey, can you write that proof on the board? What am I going to do? I'm going to draw the two pictures and then I'm going to fill in the little filler. This proof is the pictures. I cannot stress that enough. And this idea is absolutely beautiful. And if you don't think so, well, I'm sorry. I think that you're misunderstanding the idea because the idea is truly beautiful. All right, well, we're here. This is like a little technical, FTC2 is the thing that we use the most, but to evaluate things, but it really is it's just kind of an afterthought of the original statement. Okay, it's just kind of an afterthought of FTC1, and it's a technical little rabbit proof. Okay, it actually takes me more time to write the strategy than it does the proof. I'm not gonna even write the strategy. I'm just gonna write the rabbit. Okay, so want to show if G is any antiderivative of F, then the integral from from A to X of F of T equals G of X minus G of A. All right. And the rabbit, there's a magic trick and a rabbit trick here. Okay. Strategy. Note that A of X is also, and I should just say A. Subtract rabbit and sub. Here's the rabbit. A of A equals the integral from A to A f of t dt equals 0. Okay. So do we think we could do this without actually writing it out? Do you think you guys could generate this on your own from that strategy? The simple part is that I just proved that a prime of x equals f of x. Okay? That's the whole thing. So I do that, and then I combine it with this little rabbit. Here's what it looks like. Now here, I'm going to use a u instead of an x because I've got an x already. Okay. That's all I'm doing. There's no other reason I'm using a u. I'm just using a u because I already had an x. You can use an x there. You can use a t. Do whatever you want. That's fine. And now I'm just going to write it up. A of x equals a of x minus a of a. Have it. This long chain of inequality should actually start with a to x f of t dt. How do we feel about that? 1 to 5. It's just a rabbit proof. And the rabbit is this idea that I had no width if I did a of 0. I understand my head is probably blocking the thing. Oh, no, it's not. Hey. Oops. Okay. And that's it. That's the whole proof. You've now proven the fundamental theorem of calculus part 2. As I said, it's just a little cheesy little rabbit proof, right? As long as you understand that what you're doing is subtracting this 0, which is no width, the thing has no width, then you're fine. Any questions, comments, issues, suggestions, thoughts? Okay. So, wow, I'm done. What we went over today was FTC1 and FTC2. FTC2 is simply an immediate consequence of FTC1. So next time, what we're going to do is we're going to go over we're going to do initial value problems using FTC2. So there's this last bit that we're going to go over, which is the initial value problems using the Fundamental Theorem of Calculus Part 2. This is part of problem set 15. Okay, so if you look at problem set 15, if you bring it up on your computer, you will see that problem set 15 starts with, it's got basically 2 problems on it. And we are going to be going over those problems on Wednesday and how to set those up. And it's all about this idea of solving initial value problems. But instead of using the antiderivative and solving for the constant, we actually use FTC2 to do it. And you get this very clean way of looking at these things that you don't actually need antiderivatives to get good estimates for. So it's really cool. Are there any other questions? Will we be going over test content during the review sessions? Absolutely. Are these proofs going to be on the test Saturday? Okay. So what we usually do every year is we have one of the following questions. Okay. It will say, we usually give you some choice. And what we usually say is, okay, prove FTC1 without using FTC2, or prove FTC2 without using FTC1. Okay? So you'd have 2 choices on that. Or what we do is we don't give you a choice in the part, but we give you a choice in ways of doing it. So it'll say prove FTC2, and you can use part 1 or not use part 1. Or you can use prove FTC part 1, and you can use part 2 or not use part 2. Now, personally, I think those problems are cheap. Now, this semester, what we decided to do was not make you regurgitate the proof, okay? So what we're going to do instead is we made a bunch of true-false questions from the proof, okay? So it could say stuff like true or false, the A matters. And, you know, what my A is doesn't matter, right? That's right there in the proof. I get rid of my A. My A goes right here. Right, here's where I ditched my A. It may say that it may have this, A prime of X equals this, or something wrong. It could have A prime of X equals the limit. Oops, this should have a limit sign on it. Oops. Bad me, take off points. It could have this statement. It could have this statement but incorrect, right? It could have X plus H to X, which would be wrong. It could have other things could be wrong. It could have, one of these pictures here. It may have this, true or false, right? It may have this but without the H, which would of course be false. With the H, it's true. But if you know the 2 pictures, any of these details that we ask you are just come from the pictures. Does that make sense? So what we decided to do was not ask you to just regurgitate the proof verbatim. We're actually trying to figure out if we can ask you to understand the proof by asking true-false questions. Okay? Now, another question about the test, is the final content just content that we recently learned? No, the final is cumulative. And I told you this before, it's like, 60%, it's like 70% new material and 40% old material, maybe even 50% old material. And if you're wondering how that comes up to being over 100, it's because I like to ask questions like this one. Right? So if we go to my quizzes and we come here to 13B, I like these types of questions because this is old and new material. This will be on the test. I'll give you that in advance. As a matter of fact, when I write the answer sheet today, I'm probably going to just leave that on there. I'm actually going to give you the fact that question 1 is this. I think it's question 1. It could be question 2. I don't remember. I'm going to ask you to compute there's questions like these on there. I love these questions, though. I love questions like this because they ask both stuff. Let's see. Did I ask more that ask kind of both stuff? That's the same thing. Let's see. Ooh, this asks both stuff. I like these types of questions. This last condition is too hard. See what else is about. This is a good question, although it doesn't ask both stuff. Let's see. And then think about the real highlights. The definition of the derivative, the definition of the integral. Those are good questions. What else are big highlights of the class? So name some highlights of the class. So, what? 2 cops is a nice highlight of the class. The chain rule, that's nice. There'll definitely be derivatives with chains. So I will cover that when we, the question is, will the old proofs be on there? I will cover that when I talk to the other instructors. I think we cut most of them, but that doesn't mean that there's not true-false questions about them. But I need to ask the other instructors what we're saying about that. Let's see, what else is a highlight of the class? Related rates, that's a highlight. Optimization is a highlight. Those types of things. Are there any other questions? And again, on Wednesday at 7, graphs. Graphs are always a highlight. I like graphs. Okay, so again, the review session will be Wednesday at 7. If you haven't done the extra credit, the fill out my teacher evaluation, please do so. It's worth a point on your final grade. And that's it for me. So now that's 12:15, and I'm starting office hours now. So I will be in my office virtually. Let me just run downstairs and grab, at 12:30, let me run downstairs and grab some food. Anything else? Okay. So see ya.